strike a boundary, okay, the boundary can be a opaque object, or it can be a transparent object, or it can be difference between density of air also can, okay, difference between the density of air, or it can be air to water, water to air, air to glass, okay. So a boundary is what separates two medium, medium 1, medium 2. And also they must have different densities. Now, whenever a light ray strikes this one, again, I have reflection, absorption, and transmission, right? So today we'll look into the transmission, which also called refraction of light. Now, refraction happens when light passes through a transparent medium, meaning that the light can actually go through the medium. Is there any reflection happening at the boundary? Now, even though it's refraction process, right, still there will be reflection. So maybe 20 or 30% of the light being reflected, just small amount, and most of the light is being transmitted, so they can go through like this. Okay, and absorption is also there. There will be absorption at the boundary as well. But today, we're not going to talk about the reflection. We already discussed it, and we only focus on the refraction process. Now, why does light refract? Why does light refract? First, refraction, how do you like put it in simple words? What is refraction? It's just bending of light. Okay, just bending of light. Why it bends? Due to change in what? Change in speed. Light bends due to change in speed. If there was no change in speed, then it wouldn't bend, right? So when it goes from one medium to second medium, there's a change in speed. For example, if I say that the light ray go from free space to medium X. Free space is like vacuum or air, okay? Light travel the fastest in free space at the speed of light, 3 × 10⁸ meters per second. Whenever it goes from free space to any medium, light always slows down. Always slows down because it travels fastest in free space. How much is the slowing? How much it slows down depends on what type of material is this. Okay, the denser it is, the more the slowing. If you're talking about medium X, if it's like glass, then it slows down about 30%, which is quite higher. 30% reduction in the speed for glass. If you're talking about water, then that is roughly 25%, a quarter of the speed reduction. Okay. Now, one very important characteristics of the medium, which we call the refractive index. Refractive index is a property of a medium, meaning that different medium has different refractive index. Okay. Now, what is it? Refractive index is I put it into simple words, is the ability to bend light. Okay. Or you can say the ability to slow down light. Slow down light. Okay. Refractive index of a medium is the ability of that medium to bend the light or to slow down the light. If I say that the medium has very high refractive index, that means the slowing is more and the bending is more and the density is more. Okay, so symbol is N. When the N is high, speed slows down more, bending will be more bending, and then density will be higher. These are the relationship with the refractive index. Yeah. So we can say that refractive index is expressed as the speed of light divided by the speed of the medium, V. C is the speed of light in vacuum, in free space. And V is the speed of light in that medium, whatever medium is it is entering. Okay, given the refractive index of that medium, medium X. So you can calculate, right? Here, if we are talking about glass, which has a refractive index of 1.53, what is the speed that the light will travel inside the glass? You can do 1.53 equals to speed of light times 3 times 10 power of 8 over V. Okay, so 3 times 10 power of 8 divided by 1.53. That's about 1.96. Approximate times 10 power of 8 meter per second. Much slower compared to in air. Okay, now, and also this one, the refractive index is governed by the Snell's law. The Snell's law of refractions. Snell's law got two. It says that number one, it says that N equals to sine I equals over sine R. Okay, this is the first one. It says N equals to sine I over sine R. What does it mean? Meaning that if you have a medium and then the light comes from, let's say we do like from air to glass. Okay, so air to glass, air is less dense, glass is denser, right? So you're going from less dense to denser. What happened to the light ray? Less dense, we also call it rarer medium to denser medium. You go from rarer to denser, you move towards, okay, you move towards the normal. Angle of incident, angle of refraction. Here, less than I. It happened that they found that experimentally, they found that at different angle of incident, you get different angle of refraction, right? And if they go and calculate every single incident angle and every single refracted angle, they do the ratio thing. They do the sine I over sine R. Surprisingly, they found that this one ratio at any angle is the same number. They get the same number, a constant, equals to a constant. Okay, no matter what angle is the incident, okay, if you take the ratio of the I and the R, they found that you get the same value all the time. That is why they term this one as refractive index. So it is a constant, okay? It is a constant, sine I over sine R. For the calculation, we'll go to that in the next slide. Okay, so this is the first law of Snell. Now, the second law is the same as the law of reflection. Okay, that means it says that the normal line, incident ray, and a refracted ray all lie on the same plane. Okay, the reflection of light can only happen in the same plane. It cannot go to second plane. Okay, so remember the two laws of Snell. Okay, we go to the next one. Now, next slide. Yeah. Oh, yeah. Okay. Clear this one. Go to next. Okay, bending of light from the bottom of a pool, or it can be bending of a, like when you place a pencil in a glass of water, or you put a coin in a glass of water, all the same. So here we want to know how to draw the diagram. Very important, guys. The ray diagram is what give you the marks. All the time they'll ask you to draw it. Okay, so how do I draw this one? How do you see? Why when you stand beside the swimming pool, right? And then you look down, right? And then the depth seems shallower than it actually is. Right? When you go in the swimming pool and it's actually very deep, but seeing from the top is very shallow. How come? It is due to refraction. Okay, but how does the light trick our eyes? Okay, in seeing the false depth, not the real depth, right? So here how it works, right? We do a point here at the bottom. Let's say we are seeing at the floor. We are seeing the floor, so I put a point here. When you draw your light ray, right, always find a point where your light is all coming from that single point. Okay, then we draw the light ray. Now you can draw anywhere. You can put the light ray anywhere, as long as it's not like straight like this lah, because it's very hard to draw later. You want to show the bending, so you put it over here until the boundary. Here we have a boundary of air and water. Okay, you draw it until the boundary. Here's our normal. We are going from water to air, so that is denser to rarer medium. Okay, denser to less than medium. The light ray bends away from normal. Bends away. Yeah? So this one you have to remember, rarer to denser is bent towards, denser to rarer is bent away. Okay, then here I can draw the light ray, bent away. Remember to put arrow. One is not enough, draw two minimum. So another one over here, and then like this. Again, put the arrow, and here's my normal. Okay, now initially we got two light ray coming from the bottom. It reaches the surface and it come out bent, right? Come out bent. So these two light ray, let's call it light ray number 3, number 4. This is number 1, number 2. Okay, different now because this is after they bend already. Now, we are seeing the ray number 3 and number 4. So our eyes will try to find out where is this coming from. Okay, so we trace back in a straight line. You extrapolate this line using a ruler. You extrapolate. You have to draw a dashed line because there's no actual ray like this. We are just finding where is it coming from. So you have to draw a dotted dash line. Extend this one as well. You find that they meet at one point. Okay, they meet at this point here. These points should be directly on top of the object. Okay, let's call it X prime. What is this? This is the floor, right? So I'm seeing the floor. So if I see from here, then I see that the floor, the position of the floor is at this position instead of down there. Which means if I draw the position, it would be raised up like this. This is the position of the image of the floor. Okay, so is it the real position? It's not the real position, right? It's not the real, it's apparent, we say. Apparent position. The position that appears to us. Okay, so that is why we call it apparent depth. If you measure from the surface of the water, this is the depth, right? So we call it apparent depth. Apparent depth. And here you measure from the surface down to the bottom. This is real depth. Sometimes you'll see they call this one, how much is the difference here? Measure from the bottom. If you measure from bottom, the position of the object to the image, this is called the rise. How much is the rise? Okay, all measured in length. So the rise is the real depth minus the apparent depth. You get the rise. Okay, so seeing from top, you see the bottom of the swimming pool appear shallower than the real position. Same happens to a broken pencil in a glass of water. Same happen to a coin placed in a glass of water. You see, it's like being raised. Same happen when you put a big transparent glass block. You put it on like any paper with letters on it. You see the letter is being raised up. All this is due to the refraction of light. Okay, now it can be any object underwater. It can be like a fish. Okay, let's say a fish. Let's say you're seeing a fish here. Okay, you're seeing a fish at the bottom of a pond. And then the fish appear to be at this position, right? So you may have seen spear fishing, right? Spear fishing. People, they use the sharp stick spear to fish, right? They locate where is the position from outside the water, and then they strike when they see the fish, right? So they have to aim. If you aim at what you see, okay, you aim at the position that appears to your eye, then you will never get the fish. Okay, so you have to aim slightly lower than the position that you see, because what you see is the apparent depth. You have to aim the real depth. The real fish is actually down, slightly downwards. Okay, so these people, they know, okay, when they spear fish, they know they have to aim where to aim because of the refraction of the light. Okay, now same thing. You see the fish, right? You see the fish is like being raised up here. But how do you look up to the fish? How does the fish see you? Here, you see, if there's one principle of light. It says that light direction can be reversed. Okay, can be reversed, meaning that if the light is coming from here, going out, you can actually reverse the direction. I can reverse. I can do like this, like this, like this, like this, like this. Okay, because light can be reflected by the fish to your eye, and also light can be reflected by your face to the fish. So here, the light comes from your face, and then it goes into the water towards the fish. Okay, so this is, we call the principle of reversibility. Reversibility. The light path can be reversed. Because if you think about it, in reality, right, there are millions of light rays. Not only the light goes in this direction, you have light coming back and forth also. Okay, so the light ray that takes the opposite direction, it has the same path because you're dealing with the same density change. Okay, you're going from air to water, it's the same medium. Okay, so that means how the fish see you? How will you appear? How will you appear to the fish? You see, what light ray is the fish receiving? You are receiving 3 and 4, correct? You are receiving these two light rays, 3 and 4. And if I extend it, extrapolate, you see this is the position of the fish up here. But the fish is receiving light ray 1 and 2. Okay, light ray 1 and 2. So if you extend this light ray 1 and 2, you extend it backwards. Extend it backwards. Then the fish will see you up here. This is your position. This is observer here. Because remember, when you try to find the position, you always extend the ray that goes to your eye. Since the fish is receiving these 2 light rays, so we trace these 2 light rays straight to the back. Okay, when we trace it back, that cannot be bending. So we go straight, and then it sees you here, slightly above your real location. Okay, so again, you're standing here. How you appear to the fish? You are here. Okay, it's like being deflected upward. So this is the fish view of you. And your view of the fish is over here. observer's view. Okay, over here. Okay, now back to the refractive index. We have the formula of refractive index just now is speed of light over speed of light in medium, right? This is the first one. And here we have n equals to real depth over apparent depth. This is the second one that you need to remember. Okay, so real depth over apparent depth. So let's say the refractive index of water is 1.33. Okay, n equals to 1.33. What is the depth of the pool? The depth of the pool, let's say, is 5 meter. Then you can calculate what is apparent depth. Okay, apparent depth, if you see from the top, n equals to h over h. 1.33 equals to real depth over apparent depth. Okay. Right, what is this? So apparent depth equals to 3.76 meter. So for the object at the bottom, it would appear to be 3.67 meter. From where? From where? From the surface. Be careful, guys. This one is depth. Depth is measured from the surface down. So from the surface down is 3.76 meter. Be careful, not from the bottom. Okay? Normally, some students make mistake because of this one. They measure from the bottom 3.76. No, it's measured from the surface. Okay, so there you have your two formulas for refractive index. Okay, let's go to the next part. Now, here we will look at calculation of the refractive index and some things to take note, okay? Because there is one thing you have to be careful with this calculation, especially the n equals to sine I over sine R. Okay? Now, there's one condition. Some students, they are not able to get the right answer, always. They cannot get the right answers because of this confusion here. Okay, you see. Look at the diagram on the left. Here we have a light ray coming from air to glass. Okay, so we go from rarer to denser. The light bend towards, right? Bend towards. And we have incident angle 55, refracted angle 32.4. How do you calculate refractive index? Looking from this diagram, incident angle I 55 and R is 32.4. So we use n equals to sine 55 over sine 32.4. Okay, what is this value? Sine 55 divided by 32.4. Okay, you get 1 point. Okay, 1 point. Is it 6 or is it 5? Because my calculator broken, guys. Okay, I just put a number here. You correct me if I'm wrong. 1.663. It's either 6, 5, or 8 because my calculator, the screen broken. I cannot tell the difference between 6, 8, and 5. It doesn't matter. You know the answer. Okay. So whatever answer you calculated here. Wait, whose refractive index is this? Okay, be careful. This one you calculated, whose refractive index is this? We got two medium. We got air and glass. Is it for air or is it for glass? And how do you know which one is it for? Okay, you see who is doing the bending. Okay, you see who is doing the bending. The light initially come from the air, right? If the glass was not there, then the light would just go straight. So since the glass is there, the light bends. So if I ask you, who is bending the light? Your answer is the glass. The glass is bending the light. In other words, it is the second medium that is bending the light. Okay? Whatever medium that it is initially from, it is the second medium, okay, that the light travels into. The second medium that is doing the bending. So in this diagram, glass is doing the bending. So when I calculate this formula sine I over sine R, this N is the refractive index of glass, because glass is doing the bending, okay, of glass with respect to air. Again, the refractive index 1.63 is for glass with respect to air, meaning that you are calculating for glass based on air, okay, from air with respect to air. That means refractive index is always a ratio. It is what? It is always a ratio, meaning that it's always based on something. Refractive index of glass based on air. Refractive index of water based on air. It's always based on something. Okay? So, air, the refractive index based on itself is 1. Because whatever value of the refractive index of air, if you divide by itself, you get 1. Right? The ratio is 1. So that is why the refractive index of air is 1 with respect to air. Okay? So refractive index of glass with respect to air, how much? Is the one that you calculated, 1.63. Okay? Okay, yeah? So if the question asks, what is the refractive index of glass? Then you do like this. All right. More examples. We look at the second one. Okay, the second one is the same. You see the incident ray is from air. Refracted ray is in water, right? So what is the angle of incident? 90 minus 50, 40. 90 minus 61. Okay. 29. So this is R, this is I. Again, if I want to calculate the refractive index, I take sine I over sine R. What is my I? 40. Sine 40 over sine 29 equals sine 40 divided sine 29. 1.33. Whose refractive index is this? Who is bending it? Who is bending it? The second medium, okay, water is bending it. So this is the refractive index of water with respect to air. Okay, water with respect to air. Okay, take note of this. We go to the next slide, which is, for example, that incident ray is from other medium instead of from air. Okay, finding refractive index of a medium, incident ray not from the air. Okay, diagram on the left. Incident angle, refracted angle. If I do sine I over sine R, sine 20 over sine 33. What do I get? Zero 0.6279, right? So it's like 0.63. Whose end is this? Who is doing the bending? Air is doing the bending, right? Because air comes second. So air is doing the bending. That means this one is the refractive index of air with respect to glass. Okay? So if the question wants you to find the refractive index of glass, how do you find it? 0.63, is it the answer? It is not the answer. Okay? This is where many students make mistakes. It's because of this. Because this one, they are calculating the refractive index of air with respect to glass and not glass with respect to air. Okay? So what do we do here? Very simple. We use the reversibility. If you remember, just now I said that I can reverse the light direction, right? If the light coming here, going out here, it's the same as if the light were to travel backwards. If the light were to travel backwards, it would take the same path because the refractive index is the same, right? Okay, so this one I can, let me change the direction, okay? Now I change the direction just for the sake of calculation, just for the sake of finding the refractive index. Be careful you don't change the question, okay? You don't change the question. If the question wants the direction in this way, you don't like change the question, okay? So we are changing this one just to calculate the refractive index. Then we change back later, okay? Okay, so when I do the opposite direction, that means my incident ray and refracted ray change also, correct? Initially, this was my incident ray right down here. When I change the direction, that means this one become my incident ray. Okay, so if this is my incident ray, then my incident angle become 33 and not 20 anymore. My refracted angle is 20. So when I change it, my incident is 33 and my refracted is 20. Okay, so when I do the sine I, sine 33 over sine 20 equals to what? Sine 33. Again, I get 1 point. Okay, again, I cannot see the value. I just put 69. Okay, you calculate this, you correct the middle value. So sine 33 divided by sine 20 is 1.89. And whose refractive index is this? Once you reverse the direction, now who is doing the bending? Glass, right? Glass is bending it. So this is refractive index of glass with respect to air. This one and this one. That is the difference when you flip it. So in short, whenever you do the refractive index, you make sure that the incident ray is coming from the air, then you are finding the refractive index of the medium. Okay? If the incident ray is not from the air, then you are calculating the other medium, remember. So you have to change the direction of the light ray. Okay? What is the relationship between this one? Air with respect to glass and glass with respect to air. you find that for refractive index of A with respect to glass is equal to the inverse or the reciprocal of glass with respect to A. That means if you found this, you can just take 1 divided by your answer. You get the other medium refractive index. If you found this A with respect to glass, you take 1 over it, then you get the refractive index of glass with respect to A. You can also calculate it that way. Okay? This one shows the relationship between that two. Okay. This one is 5, right? So it's 5, 5. And yeah, 1.5. So the refractive index shown in your textbook or your reference book, anything, it shows that N for water, how much? Typical value is 1.33. N of glass, 1.53. N for diamond, 2.40. All this, they are refractive index with respect to A. Yes, it is the refractive index with respect to A. If you take water with respect to glass, then the number would change. It's no longer 1.33. Okay, it's no longer 1.33 because this 1.33 is based on the incident light coming from the air. So what is the key? The point I'm trying to make here is that refractive index is not a single value that is fixed to one medium. It is actually a ratio of one medium based on another medium, depending on what medium you are doing, you are referring. Yeah. Now, okay, one more example here on the right. You try it. I give you 2 minutes. Okay, I'm going to take a very short toilet break and I'll be back. You try the second one first and we look at the answers. Okay, you have the answers. This one, 50. So we reverse we want to find the refractive index of water. So we reverse this one. That means 70 is my incident. Right? This is my incident. This is my refracted. Sine 70 over sine 50. So this is water based on air. $1.23. That's the answer. Okay, we'll look at 3 examples. And after we look at the 3 examples, I will give you a short break and then we'll come back again to continue. Okay, you should be able to see my doc, my document. Example 1, example 2. Okay, so figure shows the angle of incident on air-water boundary. Calculate the angle of refraction R if the refractive index of water is 1.33. Okay, so refractive index of water 1.33 means that it's water based on air. Okay, so make sure that water is doing the bending here. So it's correct, right? So this is I, this is my R. So N equals to sine I over sine R. 1.33 equals to sine 50 over sine R. Okay, so we have sine R equals 50 over 1.33. And then we take R equals to sine minus 1. Whatever the answer that you get here. Remember to take all the decimal. All the decimal. You press answer, take all the decimal. Otherwise, your value will deviate from the answer. Okay, what is the angle? 38. Is it 38? Cannot see this one. 0.17. I think I'm going to get my my second calculator. Give me 1 second. I go and get my second calculator. I'm not sure if this one still works. Sine 50. Oh, 35, right? 35. Okay. 35.17. Okay. Example 2, using the angle shown in the figure, determine the refractive index of the what? Of the glass. So of the glass, make sure the glass is bending it. This one is not the glass bending, it's the air bending it. So we reverse the direction like this. Okay, so we have n equals to sine, this one become the incident, 90 minus 30, 60. So sine 60 over sine, we get here, right? This one, 90 minus 55. $35 equals to again, I cannot see. Okay, 1.5. 1.51. Example 3. In diagram 9, a coin is put beneath a glass block of height h. Right, so we have height h, transparent glass block. If the refractive index of the glass block is 4/3, n equals to 4/3, how high above the coin would the image of the coin be? What are we trying to find? How high above the coin would the image of the coin be? So now you put a coin under the glass block, you see from the top. What do you see? You see the coin raised up, right? The apparent depth and the real depth. What's the apparent depth? Measure from the surface of the block. This is the apparent depth. And here, real depth is h. Okay, using the refractive index, n equals to real depth over apparent depth. So 4/3 equals, what's my real depth? My real depth is h. So I put it h. This is apparent depth. I'll just put it HA, so that we are not the same, having the same symbol, HA. Okay, so apparent depth, we can find it, equals to h divided by this one. So it would be 3h/4. Okay, so h equals to 3h/4, right? We want to find the how high above the coin. So that means we are trying to find this length here, which is the rise. Okay, measure the length, measure from the bottom up, the rise. So the apparent depth is 3h/4. To find the rise, then I take the real depth h minus the apparent depth, 3h/4. Okay, rise equals to h minus 3h/4. That means 4/4h minus 3h/4. 1/4h. This is my answer. Okay, a quarter of the real depth. The rise would be a quarter of the real depth. Okay, class, I give you 3-minute break. And we come back and we continue to the total internal reflection. Huh? So just to help you refresh a bit, rest a bit, okay, before we go to total internal reflection. Okay, so now it's 26, so we continue it at 20, at 30, 5:30, okay, 5:30. Okay, so let's continue. Total internal reflection, right? Suppose that I got two medium, less dense and denser medium. Light travel from denser to less dense. I'm going to draw a light ray coming in this direction, and it bends away from normal. So go here. Let's call this light ray number 1, like this. Okay. Imagine that this is like a laser. Okay, let's say I take a laser and then I point in this direction. The light ray coming from here goes out like this. And then I slowly increase the angle of incident. Okay, I slowly move the laser further from the normal, slowly increase the angle of incidence so that the second light ray goes like this, coming in this direction, bigger incident angle, and it refracts in this direction, right? Again, I increase the incident angle more. I keep on increasing. What do I see for the refracted ray? You will see that the refracted ray keep on going closer and closer to the boundary here. Where is our boundary? This is our boundary. Here's our normal. When I increase the incident ray, you can imagine that the refracted ray move closer and closer to the boundary, and eventually it will be on the boundary. Okay, now if I draw a light ray, when the refracted ray is on the boundary, whatever angle that it is making with the normal, this incident angle here, we would say that this angle is the critical angle. Again, what is the critical angle? Critical angle is the angle if the incident light ray makes this angle with the normal, then the refracted light ray will make a 90-degree with the normal. In other words, it will be on the boundary. It will lie on top of it. Okay, on top of the boundary, directly on top of it. Now, what is this angle? Why is this angle so important? This angle is very important, okay? And we can actually find this angle. This angle can be found by using the formula n equals to 1 over sine c. Okay, so again, you have the the fourth formula of n. But this one is to find critical angle. For example, if I want to know what is the critical angle of glass, then the n for glass is 1.53. Then I can calculate the critical angle of glass. So why is this angle so important? Now, you see, let's separate all this into a few sections. I'm going to call this quadrant number 1, quadrant number 2, quadrant number 3, and quadrant number 4. Okay, so 4 sections. For light ray that is below the for light ray that is below the critical angle, okay, all the light ray will be refracted into quadrant number 2. For light ray, all the light ray, because in reality you have millions of rays, right, in different angles. So for all the rays that fall below the critical angle, they are all refracted to quadrant number 2. They will exit, they will go to a different medium. Here is denser, up there is rarer. They go to different medium. So quadrant number 2 is already a different medium than quadrant number 3. Okay, now at the critical angle, light ray, they will not go out, but it falls on the boundary, right? So let's say that the critical angle of this one is 41. Okay, so if the light is making 41, then this is the light, the path that it will take. This is 90, right? 90 here. Now, pay attention here. You see, if I increase by 1 degree, 1 degree, let's say I move the laser, I increase by 1 degree so that the light ray goes here. Now I increase by 1 degree. What is the angle here? This is 42, correct? I increase by 1 degree, 42. What happened to the refracted ray? Does it go 91 plus 1? Answer is no. Suddenly you will see that this refracted ray will jump inside. It will jump inside over here. And then what angle does it make? It will jump inside and then it will make angle also 42 with the normal here. This is ray number 4. This is ray number 4. Okay, so what has happened to the light ray? I just increased by 1 degree, just 1 or 0 point something also okay, as long as it's bigger than the critical angle. Suddenly the light ray, instead of going plus 1, 91, it jumped here inside the medium, falls in quadrant number 4. What is quadrant number 4? Quadrant number 4 is same medium as quadrant number 3, right? It's the same medium. If this is glass, then the light ray fall back into glass. It cannot exit. It cannot go out to air. Okay? And also, why is it making the same angle here? Because here we have said that the light ray has undergone total internal reflection. Total internal reflection. So it's reflection. It's the same as reflection. Okay, not entirely the same. A small difference, then later I'll talk about the difference. Okay, so basically it follows the rule of reflection. I equals to R, 42, 42. Okay, now if I keep on increasing it, okay, the next ray, I increase it more, what happened to the light? Where will it move? Imagine here, what is this angle? Okay, let me draw it here. Okay, it's getting crowded. Here, let's say I make it 60. Okay, 60. So what happened to the light ray? Light ray, refracted light ray will also make 60. Here, 60 with the normal, because I equals to R. Now, if you compare ray number 4 and ray number 5, where is the ray moving for the refracted ray? 4 to 5 is moving up, right? Instead of moving down here, it moves backward. You see, from ray number 3, where is that ray number 3? Ray number 3 is the red one, guys. Red one. Ray number 3, how it moves when you increase more, it jumps in, right? So it becomes ray number 4. And when I move further from the normal, the incident angle, I increase more, then it moves backwards to ray number 5. Instead of moving down here, it moves back up. So if I observe the movement of the refraction of light, the refracted light, starting from 0 incident angle, it is over here, straight with the normal, parallel with the normal. I slowly increase it, you will see that the refracted ray goes like this, right? This is the movement of the refracted ray until the critical angle, and then it jumps in, and then it moves backward like this. This shows the movement of the refracted ray. Now, notice that the light ray never falls in this region down here. What region? This region down here. Region where no light exists. Not exists actually, no light falls on it. Okay, because you could have light from other reflection as well. So only looking at this diagram, you see that this region has no light ray. Okay, so light cannot fall in this region, even though you move from 0 to 90-degree incident angle. Okay, now, what is total internal reflection and why is it important? Total internal reflection, why do we call it internal reflection? You see, it happened at the underside of the surface, right? Here I got glass, on top is air, right? The light ray go here, and then it got reflected back down. This is total internal reflection. It happens at the underside of the surface. It's like you are treating the surface as a mirror. Okay? This is like the water surface. Okay, let me put water. It can be water as well. Water easier. Okay, water. When the light tried to exit the water to air, then it got reflected back, treating this side like a mirror. So the light cannot go through. It cannot go out. Got reflected backwards. Okay? So that is why we call it internal, because it happens internally. It cannot go out, it happened internally. So total internal reflection. Why do we say total? Why do we say total? Okay, total is because it retains 100% of the energy. 100% of energy is retained. No energy is lost in the total internal reflection. If you compare to mirror refraction, here is your mirror. Light ray come here, bounce off. Here, 100% of energy coming, bounce off, maybe 80% left. So there's 20% of absorption. If you get 100 light ray coming, only 80 light ray is able to bounce off. Where is the 20? Gone. That is just one reflection. If you have multiple reflection, then you have many energy loss. By the time the light reaches from the other side, come out from the other side, the light already very low intensity, already very dim. The picture already very blur, very dim. So energy of light, you can think of it like brightness, intensity. Okay? So total internal reflection, why is it good? Is because it can retain the energy. Here, 100% coming in, reflected, then also keep 100%. That is why it is very, very, very useful in the industry, like the optical fiber. In the optical fiber, where they use light to carry signals to very long distances without energy loss. So the data transmission happened very fast. That is why now everybody they started using optical fibers, internet connection, telecommunications, all transmission, any type of transmission of data. Okay, so that is few things to take note, okay, on the total internal reflection and why is it different from normal reflection. Now, there are two criteria for total internal reflection to happen. First criteria is that you must bigger than the critical angle. Okay, bigger than the critical angle. And second, you must go from denser to rarer medium. Denser to rarer medium. Please take note these two. Always they will ask you, what are the two conditions? I must bigger than C, and you must go from denser to rarer. If you go from rarer to denser, like air to glass, will total internal reflection happen? It will never happen. It will never happen. So only from denser to less dense. And only if the angle is more than critical angle. Okay, yeah? So the critical angle normally is not shown on the diagram. For example, like I give you a glass, and then here's the normal. Now I draw the light ray like this. This is 42. They always want to ask you like this. This is typical questions. Okay, let me redraw it bigger. They give you a glass block, and then they give you an incident ray. This is 45. Okay, glass refractive index is 1.53. Okay, what happened to the light ray? They ask you like this, complete the diagram. How do you complete the diagram? Okay, you are going from where? You're going from denser to less dense, glass to air, right? So it already fulfilled the first condition of total internal reflection, denser to rarer. So you want to check whether there is total internal reflection or it is just normal refraction. Whether the light can go out or not. You have to check, okay? Because they will just ask you to complete the ray diagram, okay? Then you check n equals to 1 over sine C. 1.53 equals to 1 over sine C. 1 divided by 1.53. Sine inverse 40.8. So that means the critical angle for glass is 40.8. Okay, 40.8. Is it shown in the diagram? It's not shown, right? You have to calculate it yourself. You have to calculate it yourself. It's not labeled anywhere here. So common mistake, student, they see this 45 and they think, okay, oh, 45 is the critical angle. No, please. Okay, 45 is not critical angle. This is the incident angle. So the critical angle is hidden. You have to calculate yourself. Okay, so the glass critical angle is 40.8. Now this is making 45. Is it bigger or lower? It's bigger, right? So what happened to the light ray? Now, you know, instead of going out to quadrant number 2, outside the medium, it got reflected back like this. Okay, so whether refraction happened, whether internal reflection happened, you have to identify, you have to determine it. Okay, and one more thing about the total internal reflection, because I mentioned that 100% of the energy is maintained, right? So this gives the image very, very clear image. Yes, it's a very true picture. Picture formed under total internal reflection, it is very sharp and very real. Later, I will show you one phenomena that we call the ship looming, where the ship is seen floating on the sea. Okay, so it's kind of very scary. It's very shocking video. Okay, so that is one phenomena of total internal reflection, because you cannot identify whether it's fake image or is a real image. It's look as real as the real object. Okay, the image, because of the reflection. Okay, now very quick, take a screenshot of this, and I go to the optical fiber. I'll spend a couple of minutes on the optical fiber. Okay, let me go to right. So we look at a short one on optical fiber. This is based on total internal reflection. Okay, now see. What is it? Optical fiber, very thin strand of fiber. It's like as thin as your hair, very thin, that they use to transmit signal using light. Okay, so very small fiber, about less than 1 millimeter. And it is so thin that we can bend it. Okay, can bend it. Now, optical fiber is made up of 3 layers. You see, the innermost layer, the middle layer, the dashed line. Okay, the innermost is the fiber itself. The fiber itself is covered by a transparent glass, the dotted line here. And then on top of it, again, you have the outermost layer, which is a jacket. A jacket, okay, a jacket covering it. This is like a plastic jacket. It's opaque, it's opaque, just to prevent light entering. Prevent light entering. Entering from the side, because we don't want the light to enter from the side. We want it to enter from the opening here, the front. Okay, so we cover with a plastic jacket. And then the middle layer, right, is actually a transparent medium. Transparent medium, which is less dense than the fiber. Less dense than inner layer. Do you know why they must put a less dense medium outside the fiber? Light travel inside the tube, right? So for total internal reflection to happen, remember our two conditions. One is incident angle bigger than critical. Number two is you must make sure that it is going from denser to less dense. That is why we cover it with a layer of less dense medium, a transparent object, to make sure that light always go from less dense, to make sure that light always go from denser to less dense. Okay, huh? So the fiber and a less dense material covering it, and outside is the jacket. Now let's see how it works. This opening, right, is very, very small. It's like the tip of your pen. It's so small that when light enters, the light can only go in a straight line. Okay? It's so small that when light enters, it makes an angle very small with the wall of the fiber. The angle is so small that it's about 1 degree angle. Okay? Again, I repeat, because the opening is so small, right? So almost all the light ray coming in, they are making very small angle with the wall of the optical fiber. So they go in here, they strike this point. Where is the normal? This is curvature, right? This is curved, so I will draw normal 90 degree with the point here. Like this. Okay. Since it is making very small angle with the wall, then what is the incident angle? The angle of incident become very large. Is the angle with the normal, right? So this angle here, we take 90 minus the 1, we got 89. 89 incident angle, which is very large. No matter what is your critical angle, 89 definitely is bigger than your critical angle. Your critical angle can't be 90, right? Can't be 90, can't be 89. So typical value is just 40 something. So, which means that here, the light ray is going from denser to less dense, and the incident angle is bigger than critical angle, then total internal reflection happen when it strikes here. Okay, it is confirmed to happen based on the design of this. Now, I draw the light ray reflected back like this, right? Now, when it strikes this point, what happened here? Because of the curvature of the fiber is very small, again, it makes almost 1 angle degree with the wall. Because of the curvature, like this. Let's say you got two light going like this, right? One has a bigger curvature. This is like this. One is a very small curvature. Which one is making bigger angle? This angle bigger than this angle here. Okay, so bigger curvature, angle bigger. Less curvature, less angle. So this optical fiber, because of the curvature is very small, then it makes almost the same 1 degree angle with the wall. So again, if it makes 1 degree with the wall, then again, you have your normal here. Your angle is again 89. Roughly approximate values, 89. Again, TIR, total internal refraction, happen here, and your light is reflected. Go here, continue. Same happen here, go here, same happen here, here, same happen here, same happen here, same happen here. Anywhere inside the tube is where total internal reflection. Any point, every point, TIR, 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 TIR. So, what has happened here? You have seen water tube, where we can adjust the direction of water. Here, we have a tube that can change the direction of the light. Initially, the light is going in this direction, now it's coming in back in the opposite direction. It's like we have given it a U-turn. So we can call this, it's like a light tube, same as a water tube. This is a light tube. Okay, so optical fiber, the use of it is to transmit data. So the light carries the signal, transfer over long distances without loss in energy. That is the best, that is one of the advantage of it, okay, over many cable transmissions. If you see electrical transmission from the power station, they generate electricity and then they transmit to the factory, to a household, right? If you use long wire, the longer wire you use, the resistance is very high, meaning that it will cause heating. Okay, so long wire will cause heating because of the current flowing in it. It will become hot. So there's energy loss there. But if you use optical fiber, it's different. You use optical fiber, it's all just light. You're dealing with light instead of current. So there's less heating, almost no loss of energy. Plus, this one travel at the speed of light, very fast. Okay, in the telecommunication system, in the communication, internet signals, telecom system, all they use optical fiber. Okay. Still have half an hour. All right, so that basically sums up the optical fiber and the total internal refraction. This is one of the applications. There's two other applications that I'll show you quickly. This one, maybe I'll take a little bit more time. Okay. You can take some notes on this. You can take a screenshot if you want. Okay, I'll go back to the slide. Okay, if you see this picture, what is this? This is a natural phenomenon. We call it a mirage. Okay, how did it happen? And what is it? Mirage is like you're driving on the road and then you suddenly see like the road surface is like got water on it, got this pool of water. Okay, you can see from the picture. And when you reach there, it's actually dry. There's no water. Okay, so what is happening is due to total internal reflection. Basically, this is what happens here. See, usually it happens at very sunny, hot day. At the, for example, like at desert. Okay, very hot sunny day. It happens. So the reason is this. You see, I separate the air atmosphere into several layers. During the hot day, the air on top is cooler than the air closer to the ground. Here is warmer, right? Because hot day, the land heat up faster. If you remember it from your heat chapter, land heat up faster than the sea, right? So in hot day, the land gets heated up, it heat up the air close to the ground. That is why you get warm air here and cold air on top. So cold air is denser, warm air is rarer, less dense, okay? So I want you to think about a few layers like this. Going down, the density decreases. Okay, you're going from denser to less dense and less dense, less dense. So we separate into a few layers. Let's say there is this water vapor in the cloud. Okay, now what happened here? When the light comes from the cloud, reaches down close to the ground, to the layer of air close to the ground. What happened to the light? Here, we draw the normal. This is angle of incidence. it refracts away the normal or towards normal. We are going from denser to less dense, right? Remember the layer below it is getting less dense and less dense. So meaning that this light ray will bend away like this. Okay, it bends away. This is the refraction angle, correct? Refraction angle bigger than I. Now, when it reaches another layer, what is my second incident angle? Over here, I, which is bigger than the previous incident angle. Because this one, let's call it I1. Because I1 is equals to R. And since R is bigger than I, so I1 is bigger than I. Okay? So the incident angle increases. Seen from here. Okay, now continue. Here, again, it keeps on refracting away from normal. Away. And again, it strikes here. Refracts away again. Like this. Okay, what happened? Here, the incident angle keep on increasing. I2, I3. I2 bigger than I1, I3 bigger than I2, keeps on increasing at each layer until at one point, I3, let's say I3 here, will be bigger than the critical angle. Will be bigger than the critical angle. So what happened? Total internal reflection, right? So total internal reflection, that means your light ray now, instead of being refracted, instead of continue going downwards, it will be returned like this. It will be returned like this, and then return like this. So if you see from here, which is already close to the ground, okay, this one happens at very high altitude, okay, huge vast of air between the ground and the sky. So until here, it's already very close to the ground. So if you see from here, let's say you're driving, you see from here, then you see that the light ray, again, you are picking up this light ray number one. You're picking up this light ray, so I extend this. Okay, I do it like this, somewhere here. Okay, if I extend the light, because we will try to trace back, right? Where is this coming from? We trace back in a straight line, so we will see that the cloud is over here, or rather, it's not the cloud, it is the water vapor, the water droplets over here. We are seeing this one, which is a reflection of the water droplet in the cloud. Here, we see it on the ground. This phenomena is based on what? Refraction over here and total internal reflection over here. It causes the image to form on the ground. So that is why in a hot sunny day or in the desert, you see like this water pool on the road, on the street, on the road, on the desert. When you go there, nothing there. It's just an illusion. Okay, it is just an illusion. This phenomena, we call it mirage. Okay, mirage. Now, there's other phenomena very similar to this one, is also because of the refraction and total internal refraction that we call the looming. It happens almost the same manner, same concept. What is looming? Ship looming. Let me see. Let me show you a picture here. See, okay, if you want to take a screenshot, you can take a screenshot. I also recorded down the lesson. I'll post it tomorrow. Okay. Now, see this picture. The ship appeared to be floating. But is it really floating? No. Okay, it's just optical illusion again. It is optical illusions. So the real position of the ship, where is it? Is down there, somewhere down in the horizon. Okay, you see the horizon, this line over here. Huh? The ship is behind the horizon. It is due to the refraction and total internal reflection that causes it to appear to be floating like this. But the real position is down there, somewhere down in the horizon. Okay, but you cannot see it because of the curvature of the Earth. All right, so this is pretty shocking image because the image would seem very clear. Why? Is because total internal reflection retain energy. So the picture is very real. It's very sharp, bright, and real. So if it's not because of this chapter, then you would think that, okay, maybe it's something else. Maybe it's alien, right? So again, this is based on the principle mirage. How does it work? Okay, let's see. Very similar to the one that we just discussed. Okay, let me go to the next one. See, like this. Okay, now the only difference is that for the mirage just now, right? The light coming from the cloud bend in a curved shape like this, right? This one, the light is coming from the ground, from the ship, especially when the ship is at the horizon, okay, at the sea horizon. So the light coming from the ship, and then it curves in the opposite direction. Instead of curving like this, it curves like a rainbow shape. Okay, so the light ray enters our eyes like this, and we trace back the light in a straight line, so the ship appears to be floating here. This is the apparent position. This is the real position of the ship. Okay, so the only difference between the just now that one is because this one you have cooler air close to the surface of the sea and warmer air on top. Okay, cool air meaning that denser medium is closer to the sea and less dense medium is above. Why do you get that cooler air at the surface? Because in the day, the land heated up faster, right? So the sea has high specific heat capacity. So it can store more heat. So meaning that it won't heat up the air above it that much. So end up having warm air on top, cool air at the bottom. Okay, so you can actually work out the reflection. If you have cooler air, what happened to this one? You're going from cool to warmer, denser to less dense, so it bends away. Okay, each layer showing the light ray bends away and away and away. Eventually, at one point, total internal reflection happened, reflected back. So you get this rainbow curve. Okay, you get this shape, and then you see the image up there. Okay, I think I have a video for it. Let's see the video. Let me show the video. Give it a second. Oops. Let us watch some video. Okay, we are basically finished today's part lah. So we'll watch some video and before the class ends. Give me a second, I'm still finding the file. Okay, you might want to turn down your speaker a bit. Later suddenly too loud. I test the sound first, the video sound. Okay, you should be seeing the windows of the video coming up. Let's test the sound first. Oops. Okay, you adjust your volume if it's too loud. Let me know. Wait, give me a second. Okay. Mirage, same. A lot of them are fake. Some are real. Okay, you see, I think I got another one. Let me share another one. I think we got where. Yeah, short video on the Mirage.
This video surfaced out of China, and it looks like their city is floating in the clouds. Of course, we can't verify if the video is real or not, but we have seen things like this before. This is a type of superior mirage called a fata morgana, where air temperature near the surface is actually cooler than the air above. It can make objects appear like they are stacked on top of each other, or in this case, like a city floating in the clouds. The same phenomenon happens when you're driving in your car on a hot day and you see what appears to be water or something liquid on the road in the distance, or you've heard of people walking through the desert and they see water in the distance, and then once you get closer, it disappears. Light waves travel through the atmosphere from the sun straight to your eye, but they actually travel through the atmosphere at different speeds. A mirage occurs when the temperature on the ground is hotter than the air above. When light travels through the cooler air into that warmer air near the ground, the light is refracted or bent, and what your eye is seeing is not that U-shaped bend, but an illusion.
Okay. What time is it then? 6:15. Okay, so those are a few phenomena, okay, of the positive internal reflections. And we are done with this one. I'll send you the exercise on refraction of light. And next lesson, we will cover the lenses.